All right. Uh, Pardon the background noise if you hear it in the headphones, but I've got a prototype going on in the background and it's making a racket. So we'll try this out today. So, all right, we're going to get some mechanical design done today. Finally, but first we share, then we design. First we share. As soon as the preview loads, which it is not doing. So bear with me for a second. Trying out. So if you're watching this on X, the the update recently has been that these are now going out on YouTube. And I know that some people prefer to watch on YouTube and some people prefer to watch on Twitch. And so I am now on Twitch and I am on YouTube as well as X. Still waiting for this preview to load. There we go. Almost there. Almost there. 10 more seconds and we'll get going. Bear with me. So we're going to get back to design on the part tumbler today. Okay, done. All right, back to the part tumbler today. So we kind of put this aside. We had some learnings from the builds. So this was a prototype of the seat barrel or the wrap version of the barrel, which is way, way, way cheaper than the super expensive aluminum sheet stack version. And we have some build notes as well from the general assembly of things like the bearings and the motors. Um, and so we're going to go through the CAD today and get back to designing this. So there will not be much analysis. We might dump a little bit of time into specifying the motor speed, but probably now we're going to focus mostly on design here. So we'll go through this list. Essentially, this to-do list is the ground truth for what I'm focused on implementing here in CAD. So PEM nuts. I think I want to use PEM nuts everywhere. The reason for that is putting this together. I've noticed a couple things. One is reachability in these areas has been difficult, especially here with the hardware around the control box. So when you actually get to this area right here, you want to install this hardware, it can be tricky. It's not too bad if you do the build order correctly, but it's something that I think we can improve on. The problem is we're balancing cost. We're balancing cost and assembly time. So we can make this super easy to put together, but it would be $1 million to make. Like we can machine two parts out of 7075 aluminum billet and be done. But cost is the driving issue here. So we're nearly at the $300 mark, which is what our consumer competitors are at. So we have to be mindful of that. So Let's go through the list. Most nuts to PEM nuts. I think we can do that right now. Then we're going to go through and do screw clearances on attachment flanges, which are these guys. We're going to redesign this latching flexure. Access holes for the frame connection screws. I believe it's these right here, but I think switching to PEM nut is going to get rid of that need potentially. Washers on bumpers down here. So I noticed that the screw heads were small enough diameter that they were actually almost protruding through the cutout hole here. So we might increase the load distribution through the frustum of the, I always get this wrong. What is it? Frustum. 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 Yes, frustum. Frustum is the load cone from the head of the screw and the nut into the material. So we're going to use some washers to improve the performance there. Carriage bolts, yes. Carriage bolt here is going to change. I think we already did that actually yesterday, so that's done. Barrel wrap redesign, yep, that's going to be, we already did the calculations on this. This is going to be increasing the diameter. Increasing the diameter is going to make that easier to form around this these skeletons. Change the motor, easy enough, and then increase the barrel. Oh, we already talked about that. All right. So that's on our to-do list. I don't have a ton of time today. I have to end early, so this will probably only be an hour. But we'll see how much we can get through, and we will resume tomorrow. So I think the first thing I actually want to do is increase the barrel diameter. After PEM nuts. If you're wondering what a PEM nut is, a PEM nut is, 1 second. PEM nut is what these screws are terminating into. It's right here. So these are actually pressed into the part. And so when I get this part from Sen, these nuts are actually already installed. It's phenomenal. And so you might ask, well, why don't you just tap the material? And the answer is, have you ever tried repairing a messed up threaded hole in soft aluminum? And if the answer to that is yes, then you have the answer to that question. So PEM nuts are good. We're gonna try moving these around the entire assembly, and we'll see how that increased the cost. And when we get into the final stages of cost reduction here, we will reevaluate those PEM nuts and see if they provide enough assembly time when to justify their additional cost, because they do cost additional. They do cost an additional amount per part. It's not a lot. It's not, $4 or $5 per part. I think it was something like $1 or $2, maybe less. But if it saves you 20 minutes, to me, that's kind of a win, especially if you're rate producing these. It's a no-brainer if you're producing these in succession to sell. Like you absolutely want that win. If you're only building one and you're in your garage, do you want to save the $15? Maybe. So let's start moving them around. So what we'll do is we will work in a mirrored way here in this assembly. What I'll do is I'll get rid of the hardware, except for my screws. So actually we want just the We want to remove just the nuts because we're going to replace them with those pen nuts. You can see how laissez-faire I was with the installation and the placement of this hardware prior. You can actually kind of see it right now. Actually, we're going to mirror all this over anyways, so we'll just remove these bodies. Same on this side. What I'm going to do is I'm going to mirror this back over once we do it all sorted out here. So I'm just going through the assembly now and removing what will become redundant. My grid turned on. Why? Okay, so that is all of the hardware we're going to replace with pen nuts. What is the diameter we need? We need 5 point, we need this dimension essentially. Actually, we'll make that into a variable. So we'll just cite this variable throughout the assembly. You'll see how that works. So we're going to put pen nuts here. So we just change that diameter. Actually, we should do an edge check here because I know that that did us last time. Actually, I might do that right now. Or I forget. You know what? I'm already on a roll. We'll just undo these steps if we have to. Speaking of steps, I'm going to go make a copy of this. That timestamp this. Actually, no, we already did that. I think we read it to 3, so we're good. Oh, and they didn't reference the variables, but actually, yeah, I did that incorrectly. I need to undo this. Let's go check the requirements first. What I'm talking about with edge distance is when you look at the install here, there's a steadfast edge requirement from the center of the hole for a pen nut to the outermost edge. So just want to make sure we're getting that correct. Actually, because I was a good little engineer, I actually saved the part number. Actually, no, I was not a good little engineer, and I didn't save the part number. Never mind. We're gonna have to figure out what that part number is. So let's look at nuts. We're looking for pen nut. We're looking for M4 by. What's the difference between? Oh, I think we're doing this one. Here we go. And this is the one. Okay, so we care about K and M. What is K? 0.272 inches. So converting from freedom units to metric, that's 7 millimeters essentially. And I do think we're breaking that right now. So let's take a look at that. So that's saying this distance to this distance. Center up 7. We're actually good here. That's great. 7. So good on us. I think we got lucky with that one. 7. Yep. And these are fine. So we're actually good on that. So we'll actually pull that hardware in now. And I know that this is the correct one. So just copy that over. We'll use the trusty translate tool, which I abuse. We mirror this one. Actually, I'll wait to do the mirror. It wasn't an operation. Got the wrong point there, so I just fixed that. We'll do the last one, and then mirror all of this over. Okay. So we want to mirror this about this axis as well. I need my midplane for that, so let's grab that midplane. We don't want midplane barrel. We want midplane frame, which we don't have yet. So we'll make that. Curious, what's the distance between midplane barrel and frame? It's 2 millimeters. That's a skill issue. There's no good reason why these two planes shouldn't be aligned. So might come back and fix that. Actually, as a matter of fact, I'll put that on the to-do later list. So this hardware now gets mirrored over. Let's turn the barrel off. It's hard to see. So what's going on here? Nope, that's for something else. Okay, so we will, it's gonna make it easy if I just delete these. We're going to mirror, after we fix all of this hardware. There we go. Okay, so let's mirror this over now. This doesn't come along. I think it's just these. So before we do that, we should actually implement that washer here. So what is this washer thickness? 725. Move that down. We'll move this in place. We might want to bigger washer there, but for now we'll just leave that. And before I forget, let's actually test symmetry here. I'm going to mirror this just for sanity check. Yeah, they overlap totally, so they are symmetric. So I'm going to do, so I'm going to actually adjust these holes now. So we will delete this and then adjust these holes for, so they can be the, actually these are going to be, these are not going to be receiving the nuts, these are. So actually this part, I don't have to mirror. This part, I will have to change. So all of these holes now need to have the diameter changed to receive the pen nut. The cool thing is with this parameterization, you can actually upsize or downsize these holes without issue. I don't think we're going to shift away from M4 though, so fingers crossed we don't. Hopefully we won't have to do that. The software is Shaper 3D, and it's made by, I'll let you guess the name of the company. It's Shaper 3D. Runs natively on Mac, as you can see, which is phenomenal. When I started my career as an engineer, I had to use Windows. And in this year, the year of 2025, I actually get to choose. Because my FEA runs in the browser. So combination of native Apple Silicon CAD and Mac OS and browser FEA has pretty much closed the loop for me in terms of what operating system I have to use, or not close the loop, but it's giving me the option to choose. Oh, sorry for the noise. And then my analysis tool is Jupyter, which Jupyter/Python runs on Linux, Windows, Mac. It doesn't matter. Okay, so all of these holes now are sized to receive that pen nut. And watch this. Let's say we downsize it, and that new press install diameter is like 4.7. They all change. This is parametric modeling. That's parametric modeling, what I just did. This, the feature history, that is not parametric modeling. Don't be fooled. I will fight anyone on that. Okay, so we have those, we have the nuts pretty much sorted. We now can, what do we have left to do on this? I think we just mirror the hardware over now. This doesn't come along, but this does. So we mirror that. Pops in place. We forgot. We forgot our bumper. Now it's correct. So that install should be a lot less painful. I was really frustrated by that. Here, I haven't actually filmed this prototype yet. You can see the score marks and everything on the prototype. I really had a hard time with this. It was not fun at all. And you can kind of see I over torqued this screw, and you can start to see it walk off center and um, try to actually pull through. As a matter of fact, I'm willing to bet if I pull on this with a set of pliers, I might actually even be able to pull the bumper off. maybe. Yeah, you can see why we need the washer. So washer, we added it. All right. Now we mirror to the other side. So we pick up that same hardware. And we mirror about the center plane. So I have managed to keep the assembly centered on the world coordinate system center plane for the YZ axis. So I don't have to create any arbitrary midplanes for that. And then finally, actually, we want to pull over that part as well. So we will pull over the single bracket. Okay, so that is PEMNuts finished after we delete this redundant hardware. Forgot this one. Good thing we checked. Okay, so that's PEMNuts. Where else do we have hardware that could be a PEMNut? This is not sheet metal. This is machined, so I don't think we can replace this with PEMNuts, which is disappointing because this has also been painful because you have to get a wrench in here, and I have not found a clever solution for that yet. So it is what it is. Um, Same story on this side. And these are plastic screws, so this can't really be PEMNuts. So I think that's it. I think we have all the PEMNut hardware we can get in there. And I also like this because in the worst case, if you can't source PEMNuts, you can actually change these to just tapped aluminum, and you just have to be careful with it. Okay, so now we're going to increase the diameter of the barrel. The reason we're doing that is because getting the sheet the metal the how do I say this? Getting the sheet to bend to this diameter has been a challenge. You can kind of see it here, but it it wants to gap and it doesn't want to actually form to that tight of a diameter. So I think we want to increase the diameter there. And we've done the calculations to show that we can actually increase the diameter without much consequence. So we can start on that. Anecdotally, or not anecdotally, I actually have another project. Maybe it's not here. it is. I want to make sure that the part template can fit this, so I might actually use this as a guide. So in other words, I'm going to say, all right, for the new barrel diameter, it would be nice to be able to get this this part we actually want to tumble into the tumbler. Oops. Guy didn't give the export enough time to run. Go back and pick that up. Okay. Very good. There's the part. It doesn't fit. Barely. That fits. Move this out of the way for now. Did we prove that this flexure concept wasn't going to work? We couldn't actually get it to engage because the the whole flattening of this thing didn't work out well. But I'm not convinced it won't work yet. Maybe we try it one more time before we get rid of the idea. Part one of that would be extending these. So giving us a little bit less room, or a little bit more room here too. Try that out. So that's actually kind of quick. We'll just leave that design for the flexure. Now, how do we increase the diameter quickly? Is there a way to do that? I don't know that there is. I don't know that there is. Because if we scale, like I'll show you, if we scale this, right? I'm running the scale command. If we do it uniformly, let's say we make it 25% bigger, the thickness actually changes. So that went from 0.72 to 0.95, which means this doesn't actually work. There's a way to get around this if it's flat, because you can just scale it in 2 dimensions without having to scale it in 3. And then you kind of control, you can scale everything but the width. But in this case, we're spanning in 3 dimensions, so we can't do that. I don't know what the solution is there. We might have to just redraw this. So if we had to redraw this, we would do it in a rotationally symmetric way. I would make it simplest. What I mean by that is we have 1, 2, 3, 4, 5, 6 tabs. So we would take a sixth of this assembly, and then we would work on a sixth, and then we would pattern that 5 times. So that's what we'll do. And then for the additional features like this, I think we can scrape by with a sort of ugly, just taking a body out and then using that. Yeah. So I'll start copying features out that we're going to save. And then we'll just adjust for the diameter, and then we'll redraw and use those existing features. So this one's pretty easy. I'm going to just essentially create a plane at 3 points. Oh, it's picking up the mid. That's not what I want. I want this. And I want this. And then I want this if it'll let me. Hmm. I'll work around for this. All right, try again. 3 points. I'm doing is I'm creating a midplane. I'm sorry, I'm creating a plane that will be parallel with, actually, no, normal to the geometry we're going to extract from this. So that's that plane. And so now I can draw a sketch on this, project this, and then there's the feature I want to hold on to. So I can actually turn this into a body that I will copy and use later. Yep, there we go. And I will get that out of the way. So once we fix the diameter, we'll bring that back. Not fix the diameter, change the diameter, I should say. So what is the new diameter going to be? We're at, I think, 200 millimeters diameter. We want that to be, we ran the calcs on this, and I don't know that we came up with a good answer as to what a good diameter would be for this. This is really just a sort of build and test kind of thing. From our calculations here, we know the upper limit, which is to 2200 millimeters. So we're definitely not going to get that big. So let's just shoot for, let's say, increasing this by 25%. So that would be 250. So what would that actually look like? Can we actually just quickly sketch this? No. Do a quick and dirty way, potentially, to show it. So that's doubling. You don't want that. Instead, it would be 125. That would be roughly the new diameter. Interestingly, a 25% increase in diameter is going to be, let's see, so yeah, so a 25% increase in diameter is going to be, let's actually calculate that difference. So interestingly, a 25% increase in uh, diameter gives us 56% increase. So more than, so it actually, yeah, so we could actually get a 50% increase in volume, interestingly, because that squared law, the power law there, or not power law, but squared law. So that's useful. So this is definitely worth doing. So we will increase from 100 to 125. And let's pick up some geometry here for salvaging. This hatch size, for example, I think that was, we can actually just measure that by angle. Roughly 135. So 135 degrees. Just taking notes here. Actually, we'll write this in our scala draw in our notes. This is going to be difficult to copy. This detail. We'll have to figure that out later. We'll get this out of the way for now. This is also going to have to change. Just moving things out of the way that aren't in our focus right now. Okay. So let's divvy this up to 1/6, and we'll get modeling on that. So, oh, actually, first well, the hatch geometry, we don't have a copy yet. So actually we have to, um, we also have to create this plane because we have the 135 degrees saying what the opening is going to be left to right here, but we need it for the depth as well, which is this plane. So we'll save that, mirror that over out of the way. All right. Yes, it is. Okay. Then now we can get rid of this hatch for now. Actually, first let's get this hardware. We actually want this too. We want to save this. We'll, hmm, we'll save just the hardware for now. And I used the wrong plane for that. I knew it was off. There we go. Now I selected the correct midplane. We'll do the same thing for this. So we can delete this geometry. So this is also going to change. And we want to retain this feature at the center, despite our um, rotational symmetry thing we talked about. So I'm going to just extract this geometry real quick. So I think there's a way to do this with intersect. Intersect, but then I think we can, something we can do here. Actually, no, there isn't. Okay, so we're just going to make that body, and then we're going to copy it. We're going to subtract this from this. I'm going to bring this back down. And we're going to slice this body with this plane. Okay, so now we have this sort of blank. We have the geometry inside that's going to stay the same. So now we can slice this and start working on it. And so how do we want to think about this? We have, like I said, symmetry about 6 positions. So that's 360 degrees divided by 6. That's 60 degrees, which means we can pick up a plane here and then rotate that 60 degrees. Yeah, 60 degrees. And actually because it's going to be symmetrical about the center here, we're going to do 30 to 2 sides. So this will be 30. And then we'll rotate this 60. There we go. And so now we'll slice this with these faces. Almost. There we go. And so now I can delete this. Hold on to those just in case. And so now we're going to model around this. And when we're done, what we'll do is we will just quickly, I'll show you, pick up the final geometry, and we will do a pattern here of 6. Over 360 degrees. And you see what happens? We actually get the final geometry. So this is just a modeling trick to speed us up. And we said we wanted to go to 25% increase. Right now we're at, this is 100. And we want to go to 125. Wait, doubling our radius, does that, this is a very stupid thing to ask. So 2 times 200 is 400. Sorry. So 250 is the new total. Yeah, okay. So yeah, we increased this to 125. And that means we have to move this down, this PEM nut hole, by 25. Let's double check. We are, what is going on there? I want that center distance. No. Yeah, okay, that's right. Just to be careful, I'm going to pull this up 1 millimeter. Yeah, make sure we don't break any edge distance requirements. And I'm going to start deleting things that we're going to pattern later. So we can just delete this. So this is going to become 125. And this becomes 125. And then this moves. This is this. We got really lucky with this. This all becomes really easy. We just move all this stuff by 25. That's we got lucky there. So this tab has been problematic. So I'm going to redraw this. We'll leave the tab there. I mean the clearance there. So let's redraw this. Oh, I forgot we moved this up one or two. It was one, right? So we'll take a stab at drawing this tab. We'll do that by placing face there to get it flush, and we'll draw a sketch there. Why is that rounded? It's not right. I guess that is right. Something I learned from the prototype was I want this to be a little too long because that actually helps with installation. And 762 is the correct thickness, I believe. Let's double check. Yep, 762. Our mandatory ban of the spammer and Twitch. And then, okay, so then this, we're just going to give this a little too much. All 25. Maybe that's a little too much. Okay. So the way I want to model this is I think we want to just revolve this. Pick the wrong frame now, so we'll pick this one. Okay. And I think we also decided we want this to be a slot. So yeah, we'll do that. Before we do that, I'll extract this geometry from the screw. So we'll draw a slot. There's our slot. So now we will pull that through the part. There's your slot. All right, it's looking good. And finally, we are going to go into tab, and we're going to add our bend radius here. And the eagle-eyed among you will realize that indeed we are breaking some rules here. And the reason for that is twofold. And the first one is we've actually modeled this bend here incorrectly. It's actually bending on two axes, but that's okay. That's just an artifact of the way that the flattening software works, and I want to try this method out. And we'll come back and fix this if in the manufacturing part of the design we realize we need to fix that. That's easily fixable. And the second thing we're doing is we're actually protruding into the cap here. Because technically this has a bend radius. But I'm going to wave that away because what's actually going to happen is that this is not your standard seat metal bend. This is actually a hand bend. So what's actually going to happen is we're going to hand bend this around like so. So what it would look like if we did a traditional sheet bend is like this, but what we're actually going to get is something like this, and that's okay. That's why we added this slot here, because we don't actually know how accurate we have to be here. So that this should really work. Okay. So just as a gut check, let's see what this actually looks like. So we will, like I said, pattern this 6 times. It's definitely bigger. It looks right. Okay. How much time do we have left? Okay. I actually have to end here. But we will pick this back up tomorrow. So we'll see you next time.